This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome, science enthusiasts. Today's discussion dives into the exciting world of AI-powered air combat maneuvers. Imagine a world where fighter jets pilot themselves, executing complex dogfights with superhuman precision. Sounds like science fiction, right?
Not anymore. This research uses reinforcement learning to train AI agents to navigate complex environments and even engage in simulated dogfights.
Simulated dogfights? So no actual explosions, thankfully.
Yeah.
But how realistic are these simulations?
Incredibly realistic. The AI even went up against a human F-16 pilot and won.
Wow. 5-0? That's a decisive victory for the machines. What kind of technology makes this possible?
The secret sauce is a combination of twin-delayed, deep deterministic policy gradients, TD3, and hindsight experience replay.
Let's break down these fancy acronyms. First, the 2D environment experiments. What were the key challenges in getting the AI to navigate a simple, obstacle-free environment?
The initial challenge was teaching the AI to find the optimal path to a target. It needed to learn to balance exploration, trying new paths and exploitation, using what it already knew.
So it's like teaching a dog a new trick. Lots of trial and error.
Exactly. The TD3 algorithm helped manage the learning process, preventing the AI from getting stuck in suboptimal strategies.
Right. And what about adding obstacles? Did that significantly increase the difficulty?
It did, but her algorithm proved invaluable. It allowed the AI to learn from its failures, essentially turning mistakes into learning opportunities.
Clever. It's like learning from your mistakes, but on a much grander scale. Did the AI successfully navigate the obstacle course?
Absolutely. It adapted and overcame all obstacles, demonstrating its ability to generalize its learning to new situations.
The paper mentions the use of LiDAR. How did that enhance the AI's performance?
LiDAR provided crucial sensory information, allowing AI to see its surroundings and avoid collisions. It's like giving the AI a 360-degree view of its environment.
So it's not just about reaching the target, it's about doing it safely and efficiently. What other state information was fed to the AI?
The AI received a wealth of information: LiDAR, data, speed, acceleration, steering angle, and its orientation relative to the target. It was a pretty comprehensive data package.
A data feast for the AI. This sounds like a complex system.
Yeah.
How long did it take to train the AI?
Training took approximately 8 hours on a powerful GPU. Using a CPU would have taken significantly longer.
Let's delve deeper into the algorithms. You mentioned TD3. What makes it superior to other reinforcement learning methods?
TD3 addresses a common problem in actor-critic methods: overestimation of Q values. This can lead to unstable policies. TD3 mitigates this by using 2Q functions and other clever tricks.
2Q functions? Is that like having two brains working together?
In a way, yes. It provides a more robust and stable learning process.
Right. And what about her? How does it help the AI learn from failures?
Her cleverly reinterprets failed attempts as successful ones by changing the goal retroactively. It's like saying, well, you didn't reach the original target, but you did reach this other point, so let's learn from that.
That's brilliant. It's like giving the AI a second chance to learn from every experience. Does this approach have limitations?
Yes, it's computationally expensive, and the effectiveness depends on the quality and quantity of the data.
The research then moves to a 3D environment. What were the key differences in the approach?
The transition to 3D involved using a different simulation platform, Hirschfan-Chu 3D, which offers more realistic flight dynamics. The reward function also needed adjustments.
And what about the multi-agent system, the dogfights? How did the AI handle the increased complexity?
The multi-agent scenario introduced a new level of challenge. The AI agents had to learn to cooperate and compete simultaneously.
It's like a game of chess, but with fighter jets. Did the AI agents successfully engage in dogfights?
Initially, it was challenging. They used imitation learning to train one of the agents using data from an existing autopilot system.
Imitation learning? So the AI learned by watching an expert?
Precisely. This helped bootstrap the learning process, providing a foundation for the AI to build upon.
The paper discusses behavioral cloning. What is it, and what are its limitations?
Behavioral cloning is a simple form of imitation learning where the AI learns by mimicking an expert's actions. However, it struggles with situations not seen during training.
So it's like learning to ride a bike by watching someone else, but then falling when you encounter a bump you haven't seen before?
Exactly. It lacks the ability to generalize to unseen situations. This is why it was used in conjunction with other methods.
So it's not a standalone solution, but a helpful tool in the AI's learning journey. What were the results of the dogfight simulations?
The results were promising, demonstrating the potential of reinforcement learning for training AI agents to perform complex maneuvers in a multi-agent environment.
Let's summarize the key findings. What were the most significant achievements of this research?
The research successfully demonstrated the application of TD3 and HER for training AI agents to navigate complex environments and engage in simulated dogfights.
It's a significant step towards autonomous air combat. What are the potential implications of this research?
The potential applications are vast, ranging from improved flight safety to more effective military applications. It could also lead to more efficient training methods for human pilots.
It's a win-win for both humans and machines. What are the limitations and future directions of this research?
The computational cost is still high, and further research is needed to improve the robustness and generalizability of the AI agents. Extending this to more complex scenarios and larger numbers of agents is also a key area for future work.
So there's still plenty of room for improvement and innovation. What are your overall thoughts on this research?
It's a fascinating and impactful piece of work, showcasing the power of reinforcement learning in a challenging domain. It opens up exciting possibilities for the future of autonomous systems.
That was a great discussion. Thank you for sharing your insights. It was great having you. This conversation is brought to you by PhD Lite.